computer type of architecture divided into different categories now. Okay. First of all, divide into Harvard and von Neumann the architecture based on the two type of memories only: program memory and data memory. Okay. Program memory and data memory. Okay, memories are two types only: program memory and data. So whatever the RAM same only, some area program, some area data. Why data program nothing but? For example, we are understanding now the for loop is there. For loop is a program, some logic now that run the loop 10 times like that, some logic. Okay, but it has some data is there. Okay, how many time run, some I value. Okay, some data. Every programmer needs some data. Okay, the local variable, global variable, some data. Program is some logic. A equal B plus C. What A equal B plus C is? Programmer na. B is a data. A equal B plus C is a add instruction. Is a program. Okay, but some B is a some data. So every memory contain the program also and the data also. Compulsory. So program memory, data memory generally separated. Okay, sometime including also. You can see based on that one is a Harvard and tell me von Neumann architecture. Okay, you can see the best example actually now. See what the Harvard architecture. Yeah, this one is a Harvard. First von Neumann, next is a Harvard one. The first one von Neumann one. The von Neumann architecture. Von Neumann is a traditional architecture, traditional long back only. So now 8085 is a von Neumann only. 8085. Nowadays everyone follow the Harvard architecture only. What the 8051 architecture you can see now von Neumann. So the memory, I told you, memory contain the two things are there. Some area program, some area what data. Only one memory IC only. Only one memory IC are combined. Two things are there. No separate actually. Okay. So what happened? Tell me just now I told you microprocessor perform read and write operation. Okay. So everything the same IC. Microprocessor definitely perform either one action only, either program or either data. Microprocessor at the same time it cannot read the two things only, because same memory or not same area now. Okay, it cannot perform the both actions same time now, not possible, because the same memory is you can't able to perform. Okay, I put here also green color one is a data memory, red color one is tell me program is a instruction. Okay, now the microprocessor program is there on instructions are there. Okay, so now you can see here clearly. Okay, tomorrow I'll show you in the assembly language. Okay, move A comma B, some instruction is there, move A comma B. Okay, so every instruction backend processor understandable code is there. Okay, where people understand move A comma B, nothing but the move is assembly programming that you human understand only, but computer cannot understand. Computer understand what? Move backend somewhat mnemonic, process understandable code. That is called hexacode. Something, some code is there now, hexacode. Okay, the XX, I don't know what, some code is there. Okay, the code only process understanding one. This one you can store the where? Memory. Understood? No? So move A comma B the assembly instruction. You want to tell about the microprocessor, execute the instruction. The instruction backend contain the process understandable code. What is the code called? Mnemonic. This code where you can write down? Memory. Okay, correct? The code generally can call Xcode also. Xcode, no hexacode, Xcode pronounce also. This write down the memory location. Some location write down also. This area, all are XX, all are contain the program, the mnemonic, hexacode. All the process understandable code. This area called what? Program memory. The area called what? Program memory. And some other location, okay? This area called what? Tell me. Data. Data is like a 5, like a 10, something, the data memory. So your RAM, okay? Understand? Your RAM, some area, some memory location contain the what? Data. Some location contain what? Program. A pro is a move, add, sub, program is there now. Here is contain what? Data. Okay? So only one memory IC, same IC contain some area program, some area data is there. What the Harvard, what the von Neumann architecture nothing but. So von Neumann architecture have communicate the same thing, one RAM only. Only one RAM, okay, the same bus, only one bus is there, okay? Only one bus. The same bus to communicate the program memory or same bus to communicate the what? Data memory. So because of same bus, the drawback is a microprocessor one by one, either program also either simultaneously. Microprocessor cannot do at a time for the program and data. Okay, microprocessor first to load the program, next to load the what? Data. Simultaneously only possible. The traditional method on 8085 only. The latest architecture is there. So now what Harvard architecture is there? Separate bus for program memory. Separate bus for, tell me, data memory. Separate bus will be there. Two roads are there. Separate. This address line for only program. The address line for only for what? Data. The latest architecture. Two type of the roads are there. Two address lines are there. Here only one address line to communicate the program also, data also. So this one, which architecture? Which architecture? One Neumann. Oh, one Neumann architecture, this one. What a Harvard? This is Harvard. Latest one. What a Harvard? Tell me. Separate address bus for what? Tell me. Program memory.
Program and
separate address for, tell me.
Data memory.
Separate. If separate is there, your benefit is there actually. So the benefit, your people know, the microprocessor same time load the program and also same time load the, tell me.
Data.
Two things happen now, same time now. The main benefit actually, okay. So for example, the concept simple. The same cycle, same clock cycle, no time period, no, same clock cycle, microprocessor load one instruction, same time period, microprocessor also load some data. Okay, understood now? Understood. Two things happen or not now?
Yes.
So here what happened, tell me, this type of architecture support the pipeline. Pipeline is a very interesting the concept. The pipeline is a possible. Where possible, tell me? Harvard. This architecture doesn't support the what? Yeah, advanced pipeline. The old architecture support pipelining. So the meaning of pipelining. So with microprocessor execute more than one instruction. Microprocessor can execute more than one instruction within the one clock cycle. Microprocessor can execute more than one instruction. More than one instruction within one clock cycle. Within one clock cycle. So within one clock cycle to execute the more than one instruction actually. More than one instruction. So the advantage of the pipelining one. Maybe anybody know how assembly instruction works? Assembly instruction works, 3 steps are there, no? Any assembly instruction work, first step is a fetch. Second step what? Decode. Third step is what? Execute. What first step, tell me? Fetch. What is third step, tell me? Decode. What third step, tell me?
Execute.
Okay. So any assembly instruction execution, 3 steps now. Okay. How assembly instruction execute? 3 steps are there only. Fetch, decode, execution. Okay. Now 3 stages are there now. Okay. How assembly instruction execute on? Execute. 3 steps. 3 stages are there now. Fetch is the one stage, decode one stage, execute what? Another stage only. So the meaning of fetch nothing but microprocessor load the instruction. Microprocessor load the instruction. Where your program, your instruction, the program memory or not? Your instruction here. Correct no? Where the program here or not? No? Microprocessor execute the move A comma B instruction. The program here only. Microprocessor responsibility to communicate the memory, load the instruction first. The fetch no, load the instruction. After loading, still microprocessor cannot understand also. Understood no? Microprocessor, it takes some time to decoding now. Okay, decode. The exact code is there. Try to decode each and every bit. First bit this one, second bit this one, third bit this one. Decode now. Then get the clarity. Okay, this is a kind of instruction. Now once you get the clarity, decode to get the clarity confirmation. Next step is what? Execution. Once you get the clarity, no. So every bit microprocessor study internally. Okay, then clarity about the instruction. What third step? Tell me. Execution. Now start execution. Move A comma B. Execution nothing but B value transfer to what? A. B value transfer to what? A. That is execution. The job done by the microprocessor. Okay, 3 steps are there now. So the concept simple actually. No, your RAM. No, the RAM contains the program. For example, I open Word document. So Word document is a program where you can load it now. RAM. The RAM contains all the applications are not. So microprocessor responsibility to execute the Word document. That's why you are able to run the program and you are able to see now. Microprocessor responsibility to communicate the memory and what? Load the instruction. First is the fetching only. Next what tell me? Decode. Third execution. So now you can see what a pipelining. For example, first instruction, first cycle, first cycle is actually the number of cycles only. Hello? First instruction, first clock cycle tell me fetch only. Second cycle tell me decode. Third cycle tell me what? Execution. For example, my assumption is the first instruction like something move A comma B instruction only. First cycle perform tell me fetch. Second cycle tell me decode. Third cycle tell me execution. My one more instruction I'm telling add B is there something. So what happened in the first cycle, first instruction fetching, first instruction fetching, okay, that time is not do anything, okay. Second cycle tell me next instruction what tell me fetching. Next tell me here decode. So third instruction is there something, okay, like a whatever, okay, the jump instruction is there, jump, okay. So here next time what now fetch. What happened where people observe the first cycle only first instruction only. That time second one, third one not running. Second cycle what happened? First one go to what tell me decode. Every instruction of stage will be there only. First time period, first one only fetch. Second time here, second class pulse. First one go come to first fetch to what? Decode. But same time other instruction what? Fetching. Third cycle what happened? First one going to decode to what? Execution. Second one coming to fetch to what? Decode. So next third the same cycle what? Third one tell me fetching. So what happened? Tell me the meaning of pipelining. You can see third cycle only, not first only. Third cycle. Can observe third cycle to execute more than one instruction. More than what? So it's a very interesting. One instruction execution, one instruction what? Decoding, one instruction what? Fetching. Same time period. Same time period. So one instruction load the data. One instruction what? Fetching only. The fetching is a data reading one. Understood now? Is it possible? The pipelining is a possible for which architecture? Which architecture now? Harvard architecture. Harvard. That's why latest one is the Harvard one. So pipelining is very, very interesting, no? Pipelining is not there. What the story? Pipelining concept is not there. Okay.
It will take 3 cycles.
Yeah. Pipelining is in case not there. Pipeline is not there. What happened? Tell me. First instruction FDE. Then only next instruction what? FDE. Then one next instruction what? FDE, like that. First instruction completion, then only start the what? Second one. Second one completion, then only start what? Third one. There no pipeline. There no pipeline. Understand? There no pipeline. First instruction completion, entire instruction completion, fetch, decode, execution, overall. Then only start what? Second one. But here what happened? Simultaneously, because every instruction 3 stages now. So one clock pulse, one time period, one time period, duration, the microprocessor, one duration, one is execution, one is what? Decoding, one is fetching one. Understand? The very important pipelining concept is very important to understand Harvard. So everyone expecting this is very important to know. Can't see clear. Yeah. So you can see the Harvard, see everyone Harvard black diagram. Harvard correct or not? Harvard what happened? Separate bus for what? Program memory. Separate address bus for what? Tell me. Data memory. I will go to so tomorrow you see the ARM architecture. Latest one also. ARM Cortex M4. In the block diagram mentioned clearly now. ARM I will show you. Separate bus for program memory. Separate bus for what? Data memory. Separate 2 buses are there only. Okay. Separate bus now. 2 buses now. Because of Harvard architecture only. Okay. You can see also, I mentioned the computer had to separate memory, storing data in a program. Processor can complete an instruction in one cycle if appropriate what? Pipeline. First stage of the pipeline instruction to be what? Executed can be taken from program memory. Second stage of the pipeline what? Data memory. Correct now? The meaning of decoding, another instruction is a load from the memory. Load from the what? Data. First instruction is the fetching, other one tell me decoding. You're fetching now. You're fetching, you're decoding now. The fetching time is a communicate the program memory. Decode time is a communicate the what tell me? Data memory also. Decoding time. Execution is a normal within the processor only. Program memory, data memory only. One cycle. For only for what? One cycle. One cycle, program and also data also. One cycle. So decoding time, communicate the data memory. Decoding time. Okay. I will show the coming instruction to get the idea. Most of the modern computing architecture follow which architecture? Harvard. Now everyone with the Harvard is architecture. So in case von Neumann also, so processor need 2 clock cycle to implement a computer instruction. Pipelining not possible here on it. Correct now? Yes. Von Neumann pipelining is not possible. Okay, the mention clearly. Okay. So it's an old method. Method now we are not using one. So second type of the architecture, okay. So tell me, RISC and what? CISC. So RISC and CISC is a classified based on the okay the processor mechanism, okay. So you can 2 types on, okay. First one based on the program memory and data memory, 2 classification. What? Harvard and von Neumann. What second classification? Tell me based on the what? Mechanism. RISC and what? CISC. Can see everyone RISC and CISC. Everyone know the RISC full form now?
Reduced instruction set.
Reduced instruction set computer, complex instruction set. Okay, the name itself clearly the RISC contain the meaning of reduced nothing but your instructions are not complex. The meaning of reduced, your instructions are taken less number of clock cycle, no complexity, very faster. Okay, the RISC architecture execution is a very faster because no complex, no very faster on execution on that. Speed of operation very high. RISC architecture speed of operation very high. Speed of operation very better. No, the RISC no. CISC is a complex. You're more complex. Example complex mull instruction. Which one complex now? Mull. You know mull no? Mull is a complex instruction. So the example explain also. See clear now. You can see now move AX comma 10. See the move X comma 10. Move BX comma 5. Mull BX comma AX na. So can tell me the multiplication or not now? What move AX comma 10 tell me? Whenever move X comma 10 executed, AX value become what tell me? 10. Okay. Move BX comma 5 nothing but BX value equal to what? 5. 10. Mull next one tell me mull BX comma AX. Multiplication of BX into AX.
50.
Result where you can store?
PX.
X.
Okay. So they are telling clearly first to move cycle, 2 move cycles are there. First to move cycle 1 cycle, second one also 1 cycle only. But mull instruction, how many number of cycles taken? How many cycles taken? Tell me. 30. Overall, how many number of cycles you want taken? 32 cycles only. You understood? Hello? The same multiplication you are going to perform RISC architecture only. RISC architecture. Okay. RISC architecture. What is the RISC architecture program? Move AX comma 0. Nothing but AX becomes what? 0. Correct now? Next move BX comma 10. Nothing but BX value 10. 10. Move CX comma 5. X equal to 5. Begin is a label actually. Label. Where the program begin what? Add X comma BX. Loop begin. Loop what? Begin. So it's a very important the program actually, assembly program. Okay. The question is simple. Write a assembly language program, multiply the 2 number without using mull instruction. Without using Okay, no question. Write an ALP program, assembly language program. Okay, multiply two numbers without using multi instruction. The question answer this one. Without, this is very important question. Okay, see. Write an assembly language program, multiply the two number without using what? Multi instruction. Without using multi instruction. You are with multi instruction on it. With multi, you are without using what? Multi instruction on it. This is a program now. What answer is AX plus BX? The result where you can store AX. Everyone tell me yes or no? So see, what happened here? 10 into 5, no? You are finally, your simple answer here, no? I think you are 5 into 10. What answer? Tell me. 50. Simple. But here, see the instructions more only. Check it now. What AX value? Tell me. 0. What BX value? Tell me. 10. What AX value? Tell me. 10. So whenever the loop begin, every loop instruction decrement the CX value only, decrementing only. Decrement the CX value only, decrement one time. What is CX value? Tell me. 5. 5 minus 1, tell me. Loop start only, loop begin, but you go to program again back only. Next again perform also, next iteration only. Next iteration, what? Tell me. What are next iteration? What next iteration? Next iteration, what happened? AX value, tell me. 10 or not? AX value what? 10. Next 10. Iteration, second iteration now. People understood? Hello?
Yes.
The loop began, coming here on next iteration. Next time, what previous value of AX? What previous value of AX? Tell me. 10. Already BX value, tell me. 10 only. What the next one? 20. People understood? Hello?
Yes.
The meaning of loop began. The point important. Loop began, but you go to here. The loop began, but program come to what? Here. Go to here. First, everyone understood the first one clear? Hello?
Yeah, first one is clear.
Execution X value what? 0. Second one execution BX value what? 10. What first instruction? No? The source. You tell me. Destination. Source value transfer to where? Destination. Correct, everyone?
Yes.
Move instruction. Everyone understood? Yes or no?
Yes.
Okay, no, you can see, no? Your destination, then what is the source? Source register value, where you can transfer, tell me, destination. Syntax now. Okay, no, your 0 to X. Whenever this instruction run, move the data transfer instruction. Data transfer instruction. Data transfer from one register to other register. The instruction execution AX become what? Tell me, 0. This one execution BX becomes what? 10. This one execution CX becomes what? 5. The addition, add. The meaning of add, what are the operand now? AX plus BX addition, where the result store? AX. 10 plus, okay? So you can see the next iteration, next, every loop, tell me, every loop is what happened? Every loop
How
instruction
CX
decrement
is
the
working here?
CX value and go back to here only.
Sir, how CX value is decrementing here? We just used the begin only, right?
Loop instruction definition. The loop internally, every time loop here execute nothing but CX value decrementing only. Okay, we don't mention the loop definition internal now. How loop works in the assembly now. Okay, what happened? Internally decrement the what? CX value. Okay, before loop instruction, programmer decide how many time loop run only. That's why they're deciding on how many time loop running? 5 times. Okay. CX value. Okay. So here no separate instruction for like a decrement of CX only. Internal no. Process internally no, I understood. No, that the definition no internally. Okay. So that's why every loop now decrement the CX value and go to here only. Okay. 3.
Sir, a small note. Instead of CX, if I give DX, then also it will take, no?
Instead of the
CX, I give DX. So how will know that?
No, loop instruction only decrement the CX instruction, CX register only, not other register. Only
CX register. Only
CX.
Okay. Thank you.
Not other register only. Definition. Okay, loop internally every time the CX value decremented by 1 time only. Every time. Yeah, loop internal definition on that. Understood, no? Not other register, not B register, not A register. Only for which register? CX only. The definition internal. Okay. So next iteration start all. Next iteration start. What the X value? Tell me. 20. What value? Tell me. 30. 30. Next what? Tell me. No. Previous what? 3. 3 minus 1. Tell me. 2. 2. Next loop running also. Next tell me. Which value? Tell me. 30 plus 10. 40. Okay. Next what? Tell me here. 2 minus 1. Tell me what? 1. Next iteration run also. Tell me. 40 plus 10. Tell me. 50. So next which one? Tell me running. 1 minus 1, 0. So whenever answer 50 is coming, okay, so loop run. So when the loop instruction go to begin nothing but whenever CX value positive, whenever CX value positive, whenever CX 0, whenever CX value 0, then loop is a fail only. Loop is what? Fail. Once fail, go to next instruction only. Fail. So the loop is running for 5 times. How many times? 5 times only. Okay, repeat, understand now. The loop how many time run, programmer you decide the CX value. Here you mentioned 10 nothing but loop how many time run? 10 times. Repeat, understand now. So ultimately what a concept tell me without multi instruction thing, but people know the concept or not know. Without multi instruction thing, but what happened? Tell me. What happened? The same number you can addition how many time? 5 times. Understand now? First 0. Same now how many time you can do? Same number na? 10 plus 10 plus 10 plus how many time? 5 times. We get the what? 50. But we need some loop now. Understand or no? Without the loop also you can write the program, but it's lengthy na? That's not understood. Loop is there, how only for your benefit, no? You understand? You run. Loop is not there. What happened? Add AX, BX. Again also what? Tell me. Add what? AX, BX. Next tell me. Add what? AX what? BX. Like how many time writing? 5 times. Loop is there. You have program smaller, na? Loop begin. Okay, nothing but your same instruction running. Okay. So now you can see everybody. Move instruction how many cycle? Example 1 cycle. This instruction how many cycle? 1. The also how many cycle? 1. Add instruction how many time run? Loop na. 5 times or not? Tell me, sir, no? 5 times the loop because the loop no. Again run 5 times. Loop how many time run? 5 times.
5 times.
After 5 times loop is a break on now. Break. The program go to last line on now. Program break on. Okay. Total how many? Tell me. 5 plus 5, tell me. 10. 10 plus 1, 3 are 13. How many? 13. So in the RISC architecture, the addition of the 2 numbers, how many cycles taken? 13. In case CISC architecture, how many cycles taken? 32 cycles. If you are more number of cycles now, cycles are more. Okay, no, your clock cycles are more. Whenever clock cycles more, okay, power consumption is, tell me, reducing. Speed of operation also, no, your time more taken, no, speed of operation what? Decreasing. Your number of cycles are increasing, speed of operation what? Decreasing. Power consumption what? Tell me, increasing. Power consumption what? Tell me, increasing. More number of cycles are but no, the frequency directly proportional to power consumption only. Frequency directly proportional to what? Power consumption. Whenever clock increasing, nothing but what happens? Power what? Increasing. Which architecture? Which architecture? This one. Which one? Which architecture? CISC. The CISC clear. Complex. The meaning of complex. This is a complex now. Complex instruction. Which one? Which one? Complex instruction. Mul. Mul is a complex instruction. The meaning of complex is taken more number of cycle. This instruction not possible. Where? Where not possible? Where now? RISC. RISC no complex instruction like a mul. RISC no complex instructions only. Okay, no, that is the there no mul, but possible to perform the multiplication. Possible to perform the what? Multiplication. But cycles are lesser not now. The reduced instruction set computer. So less number of instructions on here.
Sir, but in CISC, we can't use this add and jump instruction over there in CISC.
Which instruction?
Add and jump loop instruction in CISC.
Yeah. Actually, they also jump only. The loop begin is a jump instruction. Actually, okay. Yeah, just to understand the loop again, you can call jump instruction also can use it now. Correct.
Then can you use these instructions in CISC architecture also?
CISC also can implement the same logic. CISC also can implement. The CISC also works on it without the null instruction, but here provide the complex instructions on. Okay, so what happened here? Main advantage. Here some advantage will be there. What advantage here? Program is very smaller, not no here.
Easy to understand.
Yeah, yes. Your program what tell me lengthy. Your instructions are more. Okay, some, but no, the cycles are what less. Advantage. Okay, understand no? Here some benefit is there. Okay, your small program is there no. You want multiply the two numbers smaller, not no. Here you want write the external, what a counter initialization, the add instruction, loop, jump instruction. But overall, they are faster or not no.
Execution time is less in RISC actually.
Yeah, very that's why RISC is a high speed of operation. Okay, very faster. So actually,
One doubt here.
Yeah, tell me. Yeah.
Yeah, in RISC we can have more instructions but less execution of time. But why don't we implement the same logic on CISC? So execution time will be reduced, right? How can we tell that this will be differentiating?
Yeah. Not only for this cycle, we discussed so many points are there. CISC and RISC architecture. For example, so many points are there. I told only for cycle. Apart from we can discuss. Okay, in the CISC architecture, how many number of instructions are there? Many number of instructions. So many are there. So many addressing modes are there. Okay, only 8085 only 71 instructions are there. Okay, in the RISC architecture, only few number of instruction, few number of addressing modes on it. Okay, here more number of instructions are there, and here one more drawback also. The CISC follow variable instruction size. Is one of the CISC method. Okay, variable instruction size. CISC follow variable instruction size. The meaning of variable instruction size, every instruction have different size only. Some instruction 1 byte size only, some instruction what 2 byte only, some instruction what 3 byte only, like the 4 byte, 5 byte, depending on instruction, not fixed size only. So every instruction variable size also is one kind of the methodology, the CISC, one kind of the factor. In the RISC point of view, every instruction fixed size only, fixed. So that will benefit actually. See here, fixed instruction size now. I will prove it in the coming session. Fixed instruction size only. The meaning of fixed instruction size, every instruction taken 4 bytes on now. Instruction size will be there no size. But move A comma B the instruction, you want load the RAM no, some size required or not no. How many number of bytes to occupy the RAM? 1 byte or 2 byte or not? If you understand no. Move A comma B, the size of the instruction is 1 byte. The instruction you want load the RAM, what is size tell me? 1 byte. So one more is there. LXI SP comma 1 2 3 4. The instruction size is 3 bytes only. So one instruction 1 byte, one instruction 2 byte, one instruction what 3 byte. Like the different size occupied now. There one drawback actually. The mechanism like that. Here every instruction what tell me here tell me. Tell me 4 byte on every instruction here. Fixed size file on it. The everything okay. So this is one of the advantage here. Fixed instruction size. So what a benefit here? So uniform memory, the location uniformly you can occupy the RAM on it. Okay. There is some kind of holes in the memory creating also. Some kind of space available on it. You are uniformly occupied. So and RISC so many features are there. Thumb mode or different features are there. RISC compared to the CISC only. Okay. So but the architecture principle, somewhat RISC better, somewhat RISC better. So mainly where the CISC is better nothing but. So the mainly wherever the power consumption not a matter. Example, your desktop computer, laptop computer, where the Intel processor, no. The power consumption not a matter. More number of general purpose computer, more number of instructions you want to execute. General purpose, no, specific purpose, there you can go to the CISC architecture. No. But wherever the power is an important factor, only few number of instruction, less amount of program, okay. Then you can go which one? RISC, the power consumption factor, especially our embedded system, okay. Our embedded boards now, wherever the mobile phone or everywhere, no, power consumption is very important. There you can go to the RISC architecture now. Okay, so that depends on the requirement. Okay, power consumption not a matter. Something, but here better the program. Here So the program is small size only. Okay, we can execute a lot of the program. Okay, so because there's no less amount of instructions. No, within 3 instructions we complete the mallow now. Yeah, okay, like that we can perform. But your power is the important factor. Your program length more only, but power is the important factor now. That's why 2 verticals in the market actually, CISC or RISC. It depends on the requirement, you can choose it now. Okay, so many differences are there. So I will cover. I'm explaining here. You'll explain all the things on. See, just now I told no, the CISC is a what variable length instruction. RISC is what fixed length instruction. Yeah, one more different. So I will show coming session. So you understood? Okay. So you see the differences also. See, yeah, no, the RISC CISC how many cycles are taken? No, 32. RISC how many cycles taken? No, 13. Yeah, same operation. So example of the CISC is a what? Intel. Which architecture? No, Intel. Intel is also called a x86. Intel is also called what? x86.
Yes, sir.
8086 onward, Intel processor is also called as x86 now. Anyone know?
Yes, sir. x86, 64.
Intel is also called as x86 now.
Yes.
Intel no, i3 is also called which one? x86 no, x86.
Yes.
i3, i5, i7, all the Intel microprocessor. What the name? Tell me. x86. Why x86? Because 8086 onwards. I'm told 8085. Next 8086 now. 8086 onwards, all architecture follow 8086 principle only. That's why 886, x86 now. 8086, 80186, 80286, 80386, 80486, Pentium 1, 2, 3, 4, core to dual core. Yeah, Intel evolution. Understood? Intel starting onwards now. So all Intel processor follow the 8086 principle only. That's why it can also call what? x86 now. x86 now the architecture follow now. So what example of RISC? What RISC example? What? ARM, MIPS, PowerPC, Spark. They all are embedded process one, embedded system we are using now. Embedded. General purpose computer is Intel architecture. Your embedded computer no, or embedded target board we are which architecture using? ARM. Understood no? So embedded board are the ARM architecture only. So the CISC and RISC is a one type of the architecture. Okay, one type of the architecture. Okay, next architecture also now. What LE and what B? Big Indian. Little Indian or tell me Big Indian. So Little Indian, Big Indian is the architecture. What is the classification based on the data transfer to the memory. Okay, so Little Indian, Big Indian is the one more category now. The computer architectures are classified different categories now. Von Neumann, Harvard, okay, RISC, CISC. What next one? Little Indian, Big Indian. Computer architectures are classified different categories now. Okay, Little Indian what? Tell me, Big Indian. One more classification. The Little Indian, Big Indian. For example, no, the memory. I'll take some example of memory. The address of memory 1000. Next location what? 1001. Next one is a 1002. Next is 1003. Some memory location. Okay, memory location. So, for example, in the C programming, write the integer into the 4 bytes. Integer x equal to. I want to load the hexadecimal data. Yeah, 0x hexadecimal representation. 1, 2, 3, 4, 5, 6, or otherwise you can call AA, BB, CC, DD. Okay, the hexadecimal number. In the C programming language, you want load hexadecimal number na 0x now. Integer. Okay, x is the variable. Okay, so the what x variable size? How many number of bytes? Tell me. Integer what is size? 4 bytes. 4 bytes. Okay. So what the meaning? How it works internally? You write the program now. How it works internally? Okay, that is a question. Okay, see how it works. So the meaning of this one, everybody understood. Okay, now the 4 bytes memory location. You can load this value or not? Yes or no?
Yes, sir.
The meaning of integer what? The integer decides the size of the memory. The size of the You can call it register only. Okay, 4 bytes, nothing but what a register size, tell me. What is a register size, tell me?
32 bits.
So 32-bit register. Okay, the meaning of this one, the 32-bit register, you can load this value now. Yes or no?
Yes, sir.
Okay, I think how many total digits now? 1, 2, 3, 4, 5, 6, 8. 8 hexadecimal digits are not now. Every hexadecimal digit equal to 4 binary bits. Yes or no?
Yes.
A nothing but what is A? What is A? A is at 10 of 1 0 1 0. Yes or no? 1
Yes.
1 0 what? Tell me. 1 0. Like that you write the all data not now. A is a 1 0 1 0. Next what? A is a 1 0 1 0. Next B what? 1 1. Next 1 0 1 1. Next
One
C. Next C. Next D. Total how many number of bits coming? How many?
32 bits. 32 bits.
You don't understood? Otherwise I want to write down.
32 bits.
Understood?
Yes, sir.
The bits are not.
Yes.
They store like that. Correct? But the 32-bit register where actually, okay? So basically people try to understand the memory doesn't have the 32-bit register actually. The memory, okay? Any RAM, there no straightforward 32-bit register. Not available. Because the width of the memory width, no? The width of the memory always tell me 8 bits. The memory unit also 8 bits only.
8 bits.
What memory unit? 8 bits. The width is always now. So any memory contain the memory location, no standard formula. The memory width is always what? 8 bits, 1 byte. Okay. So how many number of memory location? Okay, every memory location have corresponding what? Some address now? Yes or no? 1000 address contain some information, 1001. Okay. So every memory location can store maximum 8 bits only. But our requirement 4 bytes now. Requirement what? 4 bytes. Here what a question mark here? These 4 byte data, first the question mark is there. First to store DD or first to tell me AA. The question mark, okay? So here 4 bytes are there now. In the memory you can store the byte by byte only. First byte, next what? Second byte, next what? Third byte, 4 byte. The memory always can store byte by byte only. But first which byte you can take it now? The LSB na? This one tell me MSB. You have question mark is there. First to LSB store or first store what? MSB. The question mark answer is what? Tell me. Little Indian and what? Big Indian. So whenever you have 4 bytes are there, first to LSB store or MSB store in the memory, that decided by the LEN what? B. Can you see the little Indian? The simple, the meaning of little Indian. First store which one? Which one? Tell me. LSB. Which one store first? First, the meaning of little Indian architecture. Lower byte store. First lower byte now. Lower byte store now. First lower byte store. Lower byte followed by higher byte one. First lower byte store the lower address now. You know, Arjuna, next lower byte, next one tell me. CC. Next tell me. BB. Next tell me. AA. This called which architecture? Tell me. Little Indian. The meaning of little Indian architecture. Lower byte first to show the tell me. Lower address. DD first to store here. Next what? CC. Next what? BB. Next AA one. You are very important is that lower byte store lower address now. Lower byte store where can store tell me? Store into lower address now. Lower address. Lower byte store the which address now? Lower address. Higher byte store the which address tell me? Little Indian architecture. LE understanding begin the reverse one. Begin which one tell me? Reverse. Only LE understand begin the reverse one. The begin same now. Okay, no, in case no 0x AA BB CC DD. The beginning tell me. Beginning. If understand LE beginning same or not? No. Okay, begin the reverse operation. Reverse now. What are reverse beginning? What is reverse? First store which one? Beginning remind what? Most significant bit.
Yes.
First store most significant bit. MSB followed by the LSB. What? Big Indian. LSB followed by the MSB. Which one? Indian. First which one store tell me? AA. Next one tell me? BB. Next one what? CC. Next one what? DD. So what is the meaning of big Indian? Higher byte store the lower address. Lower byte store the what? The definition. Actual definition this one only. Okay. Whenever you want tell about definition of big Indian, what definition tell me? Higher byte store
At lower.
lower address. The address important actually. Lower address. Next, lower byte store which address? Tell me.
Higher address.
Very important. Okay. So higher byte store the address important. Okay. Big Indian higher byte store the first to in the if you are going to the memory now, first to write the lower to higher only, always lower to higher. Memory always the lower to higher on writing. Okay, not higher to lower. Higher to lower is a different concept. That is stack only. But every time write the memory, what happen? Lower to what? Higher. Lower address to higher address. So LE nothing but first to lower byte. Begin nothing but first what? Higher byte. Okay. The name it no need by harding. The name clear explain. Little Indian lower byte. Big Indian what? Higher byte. MSB on it. The name itself clear explain on it. So in the tomorrow you write the C programming language, no integer like that. Okay, backend happen like that only. So best example of Little architecture. The Little architecture example is one vertical Intel. Always one vertical Intel only. Other vertical what? ARM. ARM. Our embedded system, no, our embedded system, most of the architecture follow big Indian vertical. General purpose computer, which one Intel is a? Which one? It is Indian. Understood now? That depending on the architecture, no, follow. Someone follow Little Indian only. Someone follow what? Big Indian only. So in the if you write the program on the
what is the main purpose of choosing in embedded systems this big Indian? What is the difference in allocating from lower to higher or higher to lower?
What is the?
Actually, what we understood is that in our embedded systems, we adopted big Indian. But why, sir? Actually, what difference comes aligning of bytes from lower to higher or higher to lower? Is it any more useful in embedded systems? How can we say this?
Actually, tomorrow you are working on the embedded system. No, which architecture you are working on? The architecture follow L or B. You should find out. Okay.
Yes, sir.
Generally, no, that first you need to find out only. Okay. So sometime whatever we need to convert the program begin to LE also. Sometimes because we are people write the code Intel architecture. You can follow which one? Tell me LE. But same code tomorrow we are going to execute the way begin again. That time we need to converting now the program. Okay. LE to what? Tell me B. Sometime otherwise program doesn't works now because program load a different order now. So that time only we need to change the order LE to what? B. How to change the LE to B or B to LE now? We have some tools are available. Or manually also can do it. Okay, I think a shifting one now. Shift operator is there actually. Now bit of the operator with help of operator you can shifting now. Okay.
So the difference. What is the main purpose of a big Indian? That's what my question.
Yeah, not purpose actually. The traditional words, some architecture is coming to one format. Why are LE, why B? Okay, somebody follow the mechanism. Okay. So some architecture support both also. LE support also, B also supporting on someone now. Okay. So you have the answer two are there. Okay. Now big Indian, Little Indian, but most of the people are with the Little Indian only. Okay. The two solutions one now in the industry. Some architecture follow like that. That's why we study what LE, B only. Okay. Like that. Understood now?
Yeah, understood, but not clarified. What is the difference between storing of MSB in first byte or its last byte? It will give any more usefulness like that. I'm asking.
No. There no reason behind the why you can. The mainly the yeah, correct. There's no reason actually particularly.
Okay.
So why you can follow big Indian? No reason. Okay, the system, the methodology. Okay, if you store where to store the answer is LEB only. The big Indian some benefit is there, Indian some benefit is there. No reason actually. No, not like that. No reason. If you begin, yeah, understood. No reason. But conversion important actually because you are moved to one architecture other architecture now. We do conversion only. So there's no benefit at all. Okay, big Indian some benefit. We can't tell about like that. Okay, so there's no benefit on that.
Yeah, that's what my question is. Because of we have to convert again, right? The byte order. It will take more time, no? In big Indian. Why we have chosen big Indian in embedded? That's
actually there is a manufacturers follow. No, actually what happened? That is not our hand only. Nowadays, the latest architecture ARM follow the both is given the support only LE and B also because of this problem to avoid. Okay, now the latest ARM 64-bit architecture latest now support both. You can support both type of the compatibility only LE also B also, but we need to change small bit in the hardware only, so you can support it.
Okay, thank you.
Yeah. Okay, and architectures are also classified to another category also. Now the written in the beginning, one more category is there now. IO mapped IO and memory mapped IO. One more, okay. So different classification. So can you see now, yeah, next IO mapped IO and next tell me memory mapped IO. So total. So IO mapped IO next what tell me memory mapped IO. One more architecture now. One more is based on the instruction set, okay. So the types of computer architecture classified to the total 5 categories now. Yeah, this one, okay. Which one? IO mapped IO and tell me memory mapped IO.